It's the end of the renormalization day. And I realize now that many of these slides may be redundant in information. But people say a good way to learn and to teach is to have repetition. So you're going to see, again, exact renormalization, you're going to see diffusion equations, and you're going to see flows. And so you should all leave here converts into the power of the renormalization group for learning. So this is based on 4 papers. The first one last year was with John Hetman and Mark Klinger. And then the other 3 is with Mark Klinger and Alex Stapleton, who are here. Yes. And the latest paper is not yet out, but I provided you with a probability distribution of when it will be. Now, as a true Bayesian, I really should have put, some hierarchical model on what that standard deviation is. But, we'll do our best. Okay, so here we go. So we want to explore various QFT-inspired ideas for learning. And we've sort of heard them already, but let's really think about where this comes from. So data comes from some underlying probability distribution. And we are used to constructing parameterized models of such distributions, and learning is about determining the model parameters from data. That is the mantra, okay? Now, there's various assumptions within that already. If you were a traditional Bayesian, you'd be just nodding your head, you fix your model, you have some parameters, you find out what the parameters are. With the neural network crowd, also known as the youngsters, they may not think of it this way, but it is still the same. It's just that your parameters are the weights, and you have some distribution over the weights that you must learn, and actually you're just doing the same thing. It's just your function is represented through a neural network. So the traditional way we would learn is through Bayes. Bayes provides the basis for statistical inference. Now, this is the bit where I like to quiz people with their knowledge of the INSPIRE archive. So everyone knows what INSPIRES is. You go on there and you find out your publications. So who knows what the second paper on INSPIRES is? Actually, who knows what the first is? The first is Newton. Okay, so Newton comes first. It's on there on INSPIRES archive. The second paper on the INSPIRES archive is Bayes. Okay. And that's how it should be, because Bayes is really the origin of how we ever do inference and learn about the world from data. Now, what we're now going to do is then shoot forward a few hundred years and look at how, and you've heard it already, so I feel somehow, my thunder's been stolen, which is, of course, in QFT, renormalization flow describes the dependence of model parameters on energy, and Bayes is really about how model parameters depend on data. So right away, just from those sentences, we're going to be interested in investigating the relationship between data flows, which is what Bayes is, and energy flows in RG. And then we will look at this dictionary. And I think I'm going to be stronger than Miranda and not talk about analogies, but actual dictionaries between things. And then we're going to see that the amount of data takes on the role of energy from this Bayes perspective. And in all of this, the Fisher information will play the central role. Okay. So central is the work that you've just heard about, which in fact inspired us to get involved in this dictionary. I remember the Physics Meets ML series, which was organized by Jim. We had a talk on that. And then we thought, if this thing works for RG and there is diffusion in RG, we should be able to look at diffusion in Bayes. So thank you, Jim, for organizing Physics Meets ML. That was absolutely inspirational in this work. Now, so where is the connection and you've heard it all already, the connection comes through the Fokker-Planck description. That's the bridge that links RG with learning, because both RG is Fokker-Planck and Bayesian inference is Fokker-Planck. The Bayesians may be wondering, where do you see Fokker-Planck in Bayes? And we're going to get there. Okay. And then we're going to identify ERG in inverse Bayes. So for this talk, I'll introduce some information geometry basics. You've heard a lot of it before already this afternoon, but why don't I do it anyway? I'll describe exact RG and its flow, because you've not heard enough of that. When can you ever hear enough of that? And then perhaps new for this afternoon will be the idea of dynamical Bayesian inference. And then we're going to construct this map. And then, inspired by the role of Fisher information and its importance, we will look at pruning a generative model. So this is sort of what we've been listening to already, that if we've got a real model and that we want to somehow use our understanding of RG to do better, we can do so using the Fisher information. And I'll give you some pictures. The pictures are not of cats, but never mind. So, information preliminaries. Consider a parametric family of probability distributions. And I'm thinking here theta are the parameters in that family. And we have M is the space of those distributions. And then a natural basis, and this is a sort of geometric thing, is we can think of the tangent space on M in terms of these score vectors, which are these derivatives. So we've heard of the Fisher score before. For us, we want to take a sort of geometric view. And so this gives us some basis. And then the next thing we want to do, that we have this space, is construct a metric on the space. And we think of the Fisher information as actually a metric on this space. We can think of it as being given by the expectation value of the square of the scores, as written up there. Or you can think of it locally, and this is the thing at the bottom, as the infinitesimal metric, where we expand the KR divergence. Okay. So these are all equivalent definitions. The one at the top has the potential to have a slightly more global perspective, but is what it is. So for us, this quantity, calligraphic I at the top, the Fisher information metric, will really be central to the whole thing, in that it give us a scale, and it'll be a scale not associated to energy, but give us a sort of hierarchy of information with which we can then do useful things. Okay. And I guess, you know, for physicists who, like me, who spent their life doing string theory and supergravity, finding metrics is sort of what you want to do. So it just is a more natural way to think, for me at least. Okay. So now I've introduced the preliminaries of information geometry. I'm going to have to go through ERG for the third time today. And so I won't spend too long on these slides. We have a probability distribution, and we've got some parameters. And in particular, we have this lambda, which is a scale in which this probability distribution is defined. So we actually have a one-parameter family. So you think of in the space of probability distributions, you have a one-parameter family labeled by lambda the scale. At this point, we don't know it's anything to do with physical scale. We just know we've got a set of probability distributions and a one-parameter family of them. Later, physics will tell you things about scale and its relationship to short distances and all of that stuff. But at the moment, that's not there. And an ERG flow is a one-parameter family of these distributions where it's governed by this equation. Okay. And an ERG flow is a diffusive flow on the space of probability distributions. Now, the origin of it is basically that you want to preserve the partition function, so you write down those flows according to this equation. And then And again, we've all gone down the route of discussing Polchinski to describe things. We introduced what's called the Polchinski scheme. And by now we really have seen this many times. Again, for me, K is our cutoff, et cetera, G is our Green's function, etc. Okay, so I don't need to really explain this. This talk's going to be shorter than the other talks because they've already given some of my talk. So, as we say, the first term, just some Gaussian free field with a smooth cutoff. K is this thing which is in some sense regularizing the theory through cutoff. And then in Polchinski's picture, basically K gives you the whole dependence on lambda. And then you've got to solve the interaction, the action associated to interactions in order to obey that principle that the partition function is preserved. And when you do that, then you have this equation. There's a few steps to that, but whatever. And the key point is that you can rewrite this equation in the form which written as label 10 there, which you can identify with Fokker-Planck in a functional space. Okay, so it's manifestly Fokker-Planck in form, but you might worry about all sorts of things in terms of the fact it's a functional Fokker-Planck. But you know, we're not going to be too concerned by that. You can also go to other equations too. And the crucial bits of information that Polchinski give you is this thing C and this thing V, from which everything else will be derived in some sense in your equation. That's the data that you need to have. Okay. So what people did, and we're thinking here of Wenger Morris and then a whole bunch of other people, was consider different schemes and regulators. And what that really means is that you'll end up with different C's and V's. So the sort of efficient way to see this is that your ERG is this equation 10. And actually, though, depending on what your scheme is and so on, you will change the C and the V. Okay, so the data of C and V is what you're going to use and associate to particular schemes. Okay. So I did ERG, which we've heard again. It's very useful. Thank you, everyone. And now I'm going to go and take a different track, and I'm going to discuss some Bayes. And I'm just going to start with simple Bayes. Again, we have some probabilistic model. The model has some parameters, theta. Here I just gave an example of an exponential model. And we also assume some prior probability distribution, pi naught of theta, which is called the prior, on the parameters theta. So I've got to give you that. That's what I start with. And then you observe data. And then Bayes' theorem tells you how to construct a posterior distribution, I of t of theta, once you've observed the data. Okay. And here I've done it for a set of data of size t. Okay. Everyone's happy with that. It's an amazing formula. We spend our time as physicists constructing models where we have parameters, but we rarely actually directly measure the parameters. We measure something that the parameters infer, the data, and then from that we work backwards to work out what those parameters are. Okay, now, so that's fine, and then that's the posterior. But what I want to do is, instead of thinking of this as a one-shot thing, where I've got a whole bunch of data and I infer theta, I want to imagine an experiment which is running continuously, and I start the thing running, I measure data, and I infer theta. And it's keep on running that experiment, and I want to continuously update using Bayes' theorem what my estimation is for theta. And maybe it's CERN, maybe it's whatever, but t is going to end up being very large in the end. So we can think of, 10,000 measurements a day, whatever it be, many more, so that then in the end, this discrete thing of amount of data you can think of as being a continuous variable. Okay, so that's the limit we're going to be looking at, where we have a huge data set and we are continuously updating so that we can think of as t as being continuous. So in the first paper, this is what we showed, is that what Bayesian inference then looks like in this sort of continuous regime, where you're continuously taking measurements and updating your posterior, you end up with this first order equation sourced essentially by the KL divergence between roughly the true value of your parameter and actually what your current state of theta. Okay, so you can look at this equation on the right, and when theta is equal to theta star and the distributions are the same, then you stop. You don't evolve your parameters anymore because you found the true value. Okay, so what you can then do is find a schematic solution to this equation. I've written it here, equation 15. And this already tells you something, I think, quite interesting, but and it's quite intuitive. It's not a surprise. It looks like a Boltzmann distribution. The Hamiltonian is the KL divergence, and 1 over the temperature is the amount of data. Now, this is what you expect, because basically it says in the infinite limit with infinite data, it's like lowering the temperature to 0, and you basically freeze onto the true value. With very little data, I know nothing, and my estimates will fluctuate all over the place, just at like some high temperature description. Okay. So already just from this analysis, you see the connection between, in some sense, a scale and the amount of data. Okay, and the KL divergence is in some sense giving an energy to the model. Okay, now you can go a bit further and be a bit more detailed. At sufficiently late t, remember t is the amount of data, so we're into asymptotic statistics with enough data, then actually the solution is of this form. So it becomes a normal distribution with mean at mu of t, and then variance crucially given by the Fisher information, or the inverse of the Fisher information. Okay. So this is our first hint that the Fisher information also gives us a scale related to the variance in the problem. I mean, Fisher knew this, it's not a surprise. And then we can try and construct the dynamics for mu of t, the mean of this posterior distribution, and we find it a Bayes gradient flow. Okay, so in other words, we can imagine a gradient flow sourced mean given by this, and the potential will be related to the actual data set that you're getting in. Okay, good. So that's been Bayes, that's dynamical Bayes. And we've seen that, again, it has this property with things like the previous equation, which is actually, I should have said, is like the solution to the heat equation. And we've seen this whole thing in all of the talks this afternoon about the known effect of the fact that ERG is related to diffusion processes. So obviously, you want to make the link. To quote Feynman, same equation, same solutions, we just heard that. So if they're the same equations, then there must be a way to map the things onto each other. But what is the intuition? Okay. So I think it's worth going through the intuition. In renormalization, when we talk about an RG flow, we are normally throwing information away to flow to the infrared. Okay. We've got all of this stuff at high energies. We integrate out, we flow down, and then when we do for example, we saw block spin averaging, you're throwing away the fine structure detail. We've had the whole discussion about how you do that, but you're throwing the information away. Bayes is the opposite. In Bayes, I start out knowing very little and have very little data, and it's how I incorporate information. Okay. So if there is going to be a map What you need is that Bayesian statistical inference should be an inverse process to ERG flow. And actually, we already heard in the previous talk that we can think of the backward flow equation. And the backward flow equation is what's going to give us the Bayesian flow, or alternatively, the backward Bayesian is going to give us ERG. Normally, no Bayesian would want to throw information away, but you can. Okay. Right. So, as I like to tell my PhD students, find me an example. And so this is all means sort of abstract. A really good example to illustrate this is the Gaussian, okay? Because we can just calculate stuff. It's completely explicit, and you can get some simple intuition. So we consider the following Bayesian inversion problem. Basically, what we're saying is y is a variable. We've got mu, which is just some fixed number, and n is a noise given by a normal distribution, with sigma being the variance. And then you can solve that by that dynamical Bayesian inference equation exactly, which you normally can't do, but in this instance you can. And indeed, this is what you get. Okay. And the key point here is that when you compare this to something like the solution of the heat equation, then you see that you've got to identify the time with 1 over t, where 1 over t is the data. So in this sense, it's backward to the usual heat flow, but it's not that t goes to minus t or anything like that. It's actually the inverse. Okay. I realize I'm not paused for questions, and people seem not to be asleep. So are there any questions at this stage?
I guess in all three talks, I would have asked this question. I mean, one way to think about the exact RG is not really that you throw away any information. If you agree to probe the systems at low scales, you still, if you did enough experiments, you would have the information that, you know, comes from the full expansion and irrelevant operators, and you have to get those right to get that right.
Yeah.
So, yeah, could you comment on that?
Yeah, no, I think that's really important. I think the throwing away information bit is that sort of intuition, which is that Wilsonian view. And I think what's crucial for us is the fact that you can, in some sense, recreate things because you want to be able to go the other way. Because in the end, what you're doing when you're taking in data and adding in more and more data, you're flowing to the ultraviolet. So it's exactly what you said, that if you want to flow to the ultraviolet, which means actually reconstruct the detail, you should have a process that does that. That's why this is ERG, not Wilsonian. But there's still a notion of hand-wavy throwing things away. Yeah.
Maybe just to follow on to that, of course, there's the famous result of nets with dropout, which approximates, you know, Bayesian inference. So you could argue that's a form of regularization, which then does exactly that.
Yeah. I mean, there's a multitude of sins hidden in that C and V. So when you know, everyone's writing down these formal equations, and then it comes down to, and we had this from the last two talks, how you then turn that into an actual thing of something that you really do is a lot of the fun and games. Okay. Right. Okay. So maybe this is what I've just said, the posterior distribution in the inverse time parameter Tor is on the formal standard solution for the diffusion equation. The variance is like the diffusivity, that's hard to say late in the afternoon. And this suggests a very interesting interpretation of Bayesian diffusion as a sort of backwards inference. And then when we compare it to RG, this is going to be then in inverse time. And later we will get to the full dictionary where we then relate that amount of data to the scale in the RG. And we'll see that in a minute. So, and this is where, you know, there's that bit in any maths textbook where it says left as an exercise for the reader. It is in the paper, And at some point, I went through various forms of showing that the previous Bayes equation I had, and decided after as many slides in, I wouldn't do it. But for those of you who are interested in the details, it's in the paper that you can write the previous equation for Bayesian updating, which is way back. Where are you? This thing at 14, after a certain amount of work, you can show it reduces to this Fokker-Planck form. And the thing that I want to sort of emphasize again is the role of the Fisher information metric in that as being associated to the diffusivity. Okay, so this is not necessarily to show the form of the equation, but the parameter that comes out the Bayesian side is that Fisher information, or the inverse of the Fisher information actually there. So, only 5 minutes. Right. This is our dictionary when the dust settles from putting together those different sides. We've already mentioned the crucial things, this inverse time, the scale parameter, the regularized two-point function C, the inverse of the Fisher metric, the potential function actually becomes related to the log likelihood function, etc. Okay, so we have a definite dictionary by being able to identify the equations in Fokker-Planck. Okay, that was the bridge. So, I mean, okay, here there's many words. I think I've said them. If I've only got 5 minutes, I actually want to talk about how you can then use some of this and talk about something about the flavor that we've heard already, where we use some of these intuitions. And what we're going to do, we want to use the Fisher information to prune a network. So network pruning is something very practical. We have huge models. We train them and they are massively expensive and run on massive machines. But when we run them at inference, we want something efficient. People have got various methods of pruning and they're often a little bit brute force. So the argument here is, even though all of this was done with Bayes and everything else, this should be a general statement about learning, and we should take the Fisher information seriously and use it to prune a network. So what we're going to do, we're going to actually test if this works. We have a generative encoder decoder trained on MNIST. That's why I don't have cats. I'm going to have sevens and stuff. And I'm not going to tell you what the encoder is because that has some interesting properties that we're not quite finished exploring yet, but I'll discuss it later if somebody wants me to. And we're going to calculate the Fisher information for the network parameters, which are the weights, which is, a big compute task, but you can do it because we're just doing MNIST. And then we're going to look for a hierarchy in information space. So now, this is an interesting sort of other RG. Only now the RG is an information space and saying, what can I throw away? Okay. And then we are going to prune the weights that contain little information according to that. And remarkably, we find we can throw away 99.94% of the weights, which is a lot. Now, you should be suspicious. And you're right to be, because I didn't tell you how efficient this encoder-decoder was. It was very inefficient. Okay? But it is still a thing. Let's see what happens. And then we compare the outputs. So this is the generated data where there is no pruning on this very simple generative model. And it was to generate the number 7 from MNIST. And it starts out, this is sort of like, it's almost quite similar to a diffusion the way this thing works. But in the end, you can see it generates something that looks like a 7. And it's not a 7 it's been trained on, it's a sort of platonic 7, because it's some ideal notion of 7s that it's learned in MNIST. Okay. And then what we do is we calculate the Fisher information for the weights. And what you see is, and what this says is, this is actually, when I say eigenvalue significance, this is the ranking of these things. So you can see there's some very high values, but there's not a large number of them. And then it really decays. And then there's lots that are really significantly less. Okay. So we can throw away all the ones here, and I think it goes much further, and then only keep up to about 80 of those things. And it's actually already interesting that you see, remember, this is the Fisher information. It's sort of saying that the weights in your system really have got this mass gap here between all of this stuff down here, this stuff up here, and then there's some interpolating ones. Okay. And then you run it again after Fisher information metric pruning, and it's still a 7. Okay, now this is maybe not convincing because you say, well, you know, what's the accuracy really like, and so on and so forth. But I still find it remarkable throwing away 99.9 something % of weights will still give you a good generative model. Okay, and perhaps it's worth saying when Miranda was talking about the PCA type thing and the sort of values that we're looking at, this is a very similar process because the Fisher information is related to the inverse of the variance. This is a theorem. Okay. So this is just some toys that we're going to continue with, and this is the paper that's not yet out. So the proposed correspondence between ERG provides an interesting way to think of an information content in an effective theory. Bayes is a very interesting way of looking at RG, and then you can now start to go the other way, which is also very interesting. I mean, most of us here are interested in ML and AI and using physics for that. And that's what we've really discussed this afternoon. But I'm going to pose it at the end the other way, which is if we've shown this equivalence between ERG and learning in some sense, and we've made all these connections to different equations, does this approach have something to say much more about physics itself? And in particular, because it's so information theoretic in how I've done this, does it have something to say about, for example, something like supergravity? And I mentioned, I said supergravity, I mean quantum gravity. I guess too many years doing the wrong thing. So, didn't say that. Sometimes things slip out. Approaches to quantum gravity. And the reason why I say that is, you know, we're so used to in physics, this thing, when we've spoken about energy scales, we've immediately gone to this thing of doing a Fourier transform and looking at Fourier modes. I don't think you can really do quantum gravity that way because the notion of energy and gravity is very different, and I can just diffeomorph away different Fourier modes and so on. So I think it's an interesting thing to think of RG in quantum gravity as being information theoretic based rather than energy based, right? So this is now I don't really have anything more to say on that, but this is sort of the end of the day conjectures for you. Okay, so, and then as we've seen, viewing ERG abstractly as one parameter family leads over to loads of things that you can think about in terms of the logic of RG. And we are looking at various applications, everything from metabolic engineering to other things where data has not a local structure, but an information structure. Because normally we think of ERG as associated to distances. But now I'm telling you, it should be about information. Thank you very much.
Hey, this is very interesting about the pruning results. So can you tell me a little bit more about whether you can do it or so you pruned afterwards, right? So you did not prune.
Yeah.
Is there some way of pruning and before training and be still successful? And number two, can you, like, do you have a way of, 99 point whatever percent sounds very impressive, but is there a baseline comparison?
Is there a what?
Is
Sorry.
there some comparison? Is there a
No.
baseline to?
All right, let me answer one question at a time. And if I was a politician, but I'd spend long enough on the first one that you'd forget the second. So the first one was, can we do this in training? I'm going to be honest and say at the moment, no, because you see, and this comes down to, in some sense, the theory of neural networks. Why are networks got so many parameters? It's not that they need them ultimately to express the function, but if you have too few parameters, you won't find it because you're too constrained. And so you could only prune afterwards because you've by then settled down as what the important low and high information directions are. But there's a sort of spontaneous symmetry breaking goes on where it picks a direction in the neural network's parameter space, and then you can prune. If I prune before I do that, I'm less confident. But that is law. And if you have a better way, which you might, then I look forward to the papers.
Other questions?
I'm sure this question doesn't have a good answer, but
Okay. It's the end of the day. Go on.
I come from a frequentist community. Yeah,
There's always one.
yeah. And of course, we can argue about what ways we should make decisions when we're doing scientific experiments. But there are the questions of, are there principal ways of choosing priors? Are there ways of understanding how priors kind of appear? And does your framework tell us in some sense about basically the starting point of RG?
Yeah.
Like where you start. Is there anything that we learn about priors in that from this analysis?
Okay, I've not thought about this as strongly as I should, but I feel that this is tied to the fact that we do this continuous updating. So I'm going far from a flow, far and far away from where I start. So, and it feels with this RG picture that universality is also part of the story. Because in universality, it doesn't matter where I start, I flow to fixed points, etc. So that it feels like it's something like that, but I don't have theorems for you.
Hi, David. Great talk. If I understand right, you did the pruning at the end after training and then used the Fisher information. And my understanding is that because it's slow because it's a second order method. Do you know how it compares to if you just trained with the second order method, like natural gradient to begin with? Because the Fisher information is baked into that.
Yeah, no, I was discussing this also. Oh, we've got to do more work. This is why we're far from being out with this. We need to baseline. We need to compare. We need to do a whole bunch of things.
But I mean, in some sense, it's just independent of the rest of your beautiful story. It's just natural to consider the Fisher information.
No, absolutely. So, okay, I would add a couple of things. The first thing is what I really want to do, why we started with that encoder for the story, is actually we want to see the evolution as data comes in. So in other words, it's not, you could imagine that what you've got is a certain amount of data and then you found a minimum, you bring more data in and then you find something else, because that's the flow story. So it's like what I've done is really just give you a snapshot and say at this scale with this amount of data, this is what's important, what's not important. What eventually I want to do is say, as the data flows, you can see the importance of the different weights fluctuating and settling down. And that's what should happen. So what I really want is Fisher information as a function of T, where T is the amount of data. And that under training and then prune. But then it's important to get that dynamic view. And then it's a metric that's time dependent. And then you again, coming back to some sort of interesting things about flows of metrics and gradient flows. And there's another story as well, which we've discussed many times, that part of that encoder was using higher order cumulants, which feeds into what we do in a CFT, that we don't just have in the fixed point free theory. We were using 3-point functions, actually.
So I'm going to use my privilege as moderator to sneak in a question over here.
Hello.
So you mentioned that the autoencoder was kind of very general and just kind of thrown on there. Is there something to be said of like, is this kind of a replacement or I don't know, I don't want to say replacement, but is this kind of on the other end of a spectrum of like optimizing your network then? Is this kind of like doing that for you in a sense or?
Yeah, I mean, I think we just wanted an example of a generative model where we could use the Fisher to really learn something about it to make it better and we do it in a brute force way, right? I think it has the potential to be very useful. You're going to put a lot of compute up front, but in the end, if you can still get a model that works as well with not, where you've kept 1,000th of the weights. And by the way, in transformers now, this sort of thing sort of happens. We know that transformers are enormously sparse. And there's a whole literature on memory efficient transformers because you don't want to be an inference using what they did to train the thing, that's for sure. So that ability to prune, I think, could be extended to almost any model you want. And rather than do it through heuristics and waving your hands and the black boxes that people do when they do ML, you should calculate Fisher, you should see the eigenvalues, and you should do it in that informed scientific way.
There other questions?
One no.
So I haven't looked at the papers or anything, but I should before asking this. But have you looked, like when you look at the structure of your encoder or decoder, whatever, have you looked at this when you broke this down by your weights and whatnot? But have you looked at this in sort of layer-wise fashion, like where you can think of this as in some, these are different, you know what I mean? Like there may be some structure, as you alluded to earlier, that
So this is where I get to cite Jim's work and others. In the sense that you can think of we've done RG here in terms of data. There are other RG methods that people have looked at in terms of 1/n expansions, in terms of layers, a whole bunch of ways. So that's not what we do, but there are sets of people who are looking at RG applied to different expansions of neural nets, whether it be layer or number of nodes, etc. Because you just think of RG as like a perturbation theory in some sense. And what happens when you change variables? Yeah, no, we could do that. We've not done it. There's lots we could do. Okay, thank you very much
Well, let's
indeed.
thank David one more time.